I once heard that you should always look into a mirror before making a big decision, and that's because it helps you reflect. Alright, what's going on, Linear Algebra Bros? This is Mr. C here, and in this video, I am going to help us find the norm of the orthogonal projection of U onto A. Alright, let's keep in mind what this concept is. I'm going to have a vector A pointing directly to the right, A, in honor of the Fonz, and I'm going to connect a vector U to it. And let's imagine we have the non-Teletubbies version of the sun pointing directly above these two vectors as the keyboard creeps in. So what should happen in the real world is that the sun should cast a shadow of U onto A, and that shadow vector, if you will, is the projection of the vector U onto A. And it's the orthogonal projection because if you were to make another vector here, say connecting from the tip of the shadow to the tip of U, those two vectors would meet at right angles. Now what we're asked to do is find the norm of the orthogonal projection of U onto A. One way we can do that is by first finding the vector projection of U onto A. Now I'm going to write out the formula for this in this generic format. In brackets we have U dot A over magnitude or norm of A squared, which turns into a scalar which gets multiplied into the components of A. So basically what we're doing is we're readjusting the length of the vector A so that it lines up with the shadow. And there's a formula that we can use to help us figure out what scalar we would need to multiply to A in order to make that happen. And that formula is given inside of this set of brackets. It's a bougie scalar. Alright, marching on forward. Let's bring in all these vectors. Vector U, 404, dotted with the vector A, -2, 3, -2. And then the norm of A, we'll have to square -2, we'll get 4, add it to the square of 3 to get 9, add it to the square of -2 to get 4 again. Now don't forget, there is that power of 2, which will have to go on the square root, eventually canceling it out. And now the components of A, -2, 3, and -2. Now simplifying this down, okay, the numerator, if we form the dot product there, it's going to be -8 plus 0 plus -8. That's going to give us -16. Now down here, 4 plus 9 plus 4 is 17. And the square root and the power of 2 will cancel, leaving us a denominator of just 17. So it turns out that if we wanted to readjust the length of the vector U so that it has the same length as the projection of U onto A, the length of A so that it has the same length as the projection of U onto A, I'm sorry if that was duplicative, we would have to multiply the components of A by -16 over 17. Now let's go ahead and distribute that in to get the cleanest format of this projection vector. It'll be 32 over 17 for the first component, -48 over 17 for the second component, and then 32 over 17 for the third component. Now, is that what they asked us for? No, but it's a big stepping stone, right? They want the norm of this projection vector. So let's move on and see how we would do that. Well, the norm of the projection of U onto A can be rewritten so that we have the component form instead of the notation. And of course, we could apply the formula for the norm of a three-component vector, much like we did up there when we were finding the norm of A. But I want to do a little quick recall statement over to the right here. This was a property that was at the bottom of page 1 of section 3.2, I believe, where it said the norm of a scalar multiple of a vector u can be rewritten as the absolute value of k times the norm of u. So in other words, we can more or less factor this k out, provided we surround it in absolute values, just in the just in case the value of k is negative. And keep in mind, norm is the measure of a length, so it should always be in positive units. Now, if we take a look up here, that's a rewrite of our projection our projection vector. All right, it's the step before we got to our final answer for its components. So what I'm alluding to is this. Let's maybe use this version of the projection vector when we're calculating norm. So we have negative 16 over 17 times the components negative 2, 3, and negative 2, which would allow us to apply this formula in the recall statement. In other words, we can take negative 16 over 17 out, provided we take the absolute value of it, and multiply that to the norm of the vector with components negative 2, 3, and negative 2, which are the components of A. Now the absolute value of negative 16 over 17 is positive 16 over 17. And then we already calculated the norm of A with our projection calculation, and that turned out to be the square root of 17. Notice the square root is still in there, and that's because there's no power of 2 on this norm notation, so just something I wanted to point out. And that, my friends, is where the pain and torture, fun and excitement for this solution video ends. Let me know if you have any questions. Otherwise, thanks for watching, and I hope your weekend is completely normal. I'm sorry, that was bad. That was a stretch. All right, I'm signing out. Have a good day, folks.